We've seen how pointers work, but where pointers really get their power is they allow us to allocate memory as we write our programs. So we don't need to know everything we need before the program starts. We can allow the program to determine what sort of memory it needs to use. Let's start off with a simple example. We'll do an int pointer. And we'll allocate memory for that using the malloc function. So the malloc function takes a parameter that's the number of bytes you want to allocate. Now, I know an integer is 4 bytes on this machine, but what if I'm not running it on this machine? So it's always best to do size of the data type you're looking for. So this is going to allocate 1 int's worth of memory, however many bytes that is. Now, before I use this integer pointer, I need to check to see if it is valid. So I'm going to check to see, is it null? If it's null, then I want to put an error, and I'll use puts or fputs. And realistically at this point, I want to go ahead and just exit the program. So I'll do exit -1 to indicate something bad happened. The program is going to quit. So what this does is it says, quit the program immediately. The error code is -1. That lets the operating system know something bad happened. So now, if I want to use this, and let me just say here that because I'm going to allocate a lot more in this file. So now to use this, and at this point I'm safe because if there was a problem, I've exited. I can say that is equal to 10, and then I can print that's going to be some memory location that it holds. And then it has an address. So let's just see what that is just so we can see the difference. And let's dereference it. Hopefully by now you know what each of these do. If not, make sure you review the other pointer videos. So here we have int pointer. We need to cast it to avoid pointer, just to avoid the warning. And I will admit that I don't like casting it just to avoid the warning, but on the other hand, I don't want to ignore warnings in these class examples. So that's definitely a warning though that's safe to ignore. So here's the address where the variable int pointer is stored, and then we'll print what int pointer is. So it looks like we forgot to declare malloc, and that's a library function, so we'll pull in that header file. And then we also looks like we have some issues with on line 9. We have a extraneous slash there. So malloc is in standard lib.h. So when we pull that in, we'll get that forward declaration. Did I not save the file? So too few arguments for fputs. Yes. So fputs is different from puts, which automatically puts it on standard out. I want to write that to standard error. So that's the error stream, and now it looks like it works. So let's run it. And so we can see that input pointer is holding this address. Notice that's nowhere near where int pointer itself is allocated. And again, that's because this is allocated on the stack. This will be heap memory or from the memory store. Here we see that we've stored 10 in that variable location. Wherever that is, it now has the value 10 inside there. So we can also allocate an integer array So I think nums is the name that we've been using for arrays. And so we're going to say nums is equal to malloc. And let's make an array of, well, let's use a symbolic constant here. We'll say 10. And the reason we're going to use a symbolic constant is we don't want to remember how big this array is. So it's going to be count times the size of an int. And I don't want to just say count because that'll just give me 10 bytes. Well, an array of 10 integers takes up more than 10 bytes. And remember, with that, since there's no bounds checking, it means that I'm going to have problems of some sort. Here we're going to assign those as values. So we're going to dereference each integer. So nums is the first one, then nums plus 1 plus 2, and so forth. So we'll put in a number. We'll call it just 10 times ii. Let's just make it 11, just so that we don't get that confused with count itself. Now we've allocated nums. But the size of nums let's see what that is. And let's go ahead and print nums as well. So we're going to say nums plus ii, and then we're going to dereference that. That'll give us the actual value. And one thing that we forgot to do before, we always want to make sure we free our memory once we're done with it. So we'll free nums. And we also forgot to free our int pointer. And it knows what memory it allocated to that, so I don't have to deallocate each individual integer, because really it doesn't care. It just knows there's a block of memory. So when I say free, it's going to free all the memory it allocated for that variable. And there's a slight difference we'll talk about when we get to C++ that we'll need to write destructors that do some additional work because they might allocate more memory. When we instantiate a new object, sometimes they allocate memory themselves. But for C, that pointer is pointing to all the memory that was allocated for it. So let's see how that goes. Oops, we said num, not nums. And we declared nums, right? Yeah, so nums is an int pointer. So I'll look for anywhere I have num but not nums. That's the last place. So when I print this, you can see that I've allocated that memory. One thing to keep in mind, though, is that free doesn't actually free the memory or clear the memory. So here I freed everything. Notice it still printed those values out. We did get a little bit of corruption, it looks like, with some of those earlier values, but some of these later ones are still there. So we're not zeroing it out. So we might want to, for security's sake, go ahead and once we free memory, we might want to clean it up as well. But we won't do that now. Just something to keep in mind. Okay, so now let's allocate a character or a string. So here's my character pointer. And let's allocate that down here. So to allocate a string, it's going to be just like we allocated a character array. We're going to allocate some size, so we'll just say count, times the size of char. Now, if I put 10 in there, it would work because on this system, a char is a byte. 10 bytes is enough. We really need to put this anytime we do malloc, so I'm going to put that there. This is, and I'll put this here as well. Again, it's good practice so that you don't use memory that's not valid. So if we have a problem, it's going to exit immediately. So now I can do a string copy into pointer. I'll say hello, and I'll say count. So you want to be careful when you do a string copy. It's going to copy this many characters. If there's no null terminator here inside that many characters, we're going to run into a problem. But we're going to be safe here because hello is well within the boundary of what we can do. Let's go ahead and write that string. And again, we can use put s here. Put s by default is going to go to standard output. So we could say f put s and go to standard error if we wanted to, but put s will work in this case. And let's go ahead and free it because we're done. Oops, string copy is in string or string.h. And I need to save my file. So there we go, there's hello. Now, I freed the pointer. If we immediately put it again, notice we get a null terminator. So it did happen to clear in the meantime there, but there's no guarantee that'll happen, so don't rely on it. If we really want to make sure nothing happens there, we can just set that to null. Suppose we want to write a function that allocates memory. So we're going to write a function that's going to allocate a new string with the same characters as the parameter str. And so my function is going to return a character pointer. It's going to allocate a string, or I'm going to call it allocate string. And I'm going to create a const char pointer str. That's my parameter. Now, the const there ensures that we don't modify str. Here's what we're going to do in this method. Now, we're making a big assumption. We're assuming that str is a valid C string so that it's null terminated. And the reason is to determine how many bytes we want to allocate, we're going to get a size that's going to be the string length of the string. And then we're going to add 1 to that for a null terminator. Then we're going to create a new pointer that'll be for a new string, and we're going to allocate size characters. Now, of course, if new string is null, then we have a problem. Now, we have a philosophical question that we need to answer here, and that is, what do we do if it's this error? We don't want to exit the program. That's not really nice for someone to call a function, and then we exit from that function. So we're going to leave new string alone. It's going to be null. So if it's null, we're going to write a message to the error stream. So they're not going to get it in the console if they're redirecting error somewhere else. But we're not going to do anything else with that new string pointer. We're going to return that new string pointer as is. So we're going to return new string. So we need an else condition where we actually do the string copy. And here we're going to do a string copy into new string from string, whatever the size is. And you'll notice since we're assuming string is a valid C string, we're using string length to get its size. And then that means that this copy will work because the size is sufficient. The size is longer than string, so there's definitely a null terminator before we get to size. So that will work. Here we're allocating the string. Here we're getting the size. You may think, well, that's kind of weird to return a local parameter as a return. And we would never want to return a pointer to the local parameter. But new string is a pointer. It's a variable pointer. It's going to hold an address. That address is going to be to this memory that we allocated. While new string is a local variable, the memory it points to is still available after we return from the function. Let's do a forward declaration for this. And let's see if we can get this to work. So we already have a string pointer, and we freed the original memory there. So let's say pointer is equal to allocate string. This is a test. Let's print this. So we have the address, the length of the pointer using string length, and we need to free pointer. Don't forget, because we didn't do it in the function, of course, because we want to pass that function. But that pointer knows what to free, so this will work. But it is a little bit of a problem because the user of our function is going to have to know to free that memory. So we have a bug. And I think that was a colon, not a semicolon. So it looks like this is a test, works very nicely. So let's do this again. Actually, let's do it twice more. I'll just do one character. In fact, let's do this. Let's allocate an array. Okay, granted that's not a sentence, but so here instead of passing in a string literal, we'll pass in a string, an array string, and you'll see that each time that works just fine. Let's use the print here, since that's what we've seen before. So that should clean up our output a little bit. And so you can see here we have the different strings that we allocated in different ways. Although our output is still a little messy. So we talked about how malloc doesn't clean the memory. So let's see an example of that now. So we have that character pointer. We can use that again. And let's do 32 bytes of memory. And let's print. Here's the address. So now we're going to print memory byte by byte. And there's a couple ways we can do this. I think probably the easiest way, though, is let's just print one hexadecimal digit for each value there. And that is going to be dereferencing pointer plus II. Here what we're doing, we've allocated 32 bytes of memory, and then we're going to print them out one by one. That's a character. So we'll cast that to an unsigned int just to avoid that warning. And then I ran into the comma operator. There we go. So I think that should be fixed now. Okay, so if you can look there, this memory, we have a bunch of zeros, but then we have a bunch of these random numbers too. If I want to have clean memory, then I can use calloc. And that does clean the memory. So let's do the same thing we did here. 1, 2, 3, 7, I think 7 lines. I want to copy. And instead of malloc, I'm going to do calloc. And calloc works a little bit differently. I need to tell it not how many bytes, but how many units. And so the first parameter is the number of things I want to allocate, and then their size. So you can almost think of this as allocating an array. And so let's print that out. And you can see when we use calloc, we get all zeros. So typically, you don't need to call calloc if you're going to use all the memory. Malloc is faster because, hey, we're saying, hey, look, you can use this memory. You're not taking the time to go through and clean it up. And you know what? I did not free pointer there. And this isn't necessarily the case, but you can see that we allocated 2 different memory locations. So that's pretty bad. In fact, and you can notice that that's 20 bytes later. So that's just in memory. I don't have a pointer to it. So I need to free that up. And I'm kind of curious if it's going to give me the same location. No, it still actually gave me a different memory location, but now this is freed and we can reuse that later. So just one of the little things you have to be careful of when you're dealing with pointers. Okay, so I realize that this example is going long, but there's one more thing that we want to talk about. Suppose I have a structure. And that it's going to hold an integer and a string. Well, actually, it's not a string, it's a character pointer. So we're going to need to be careful here. So to allocate this struct, first I need a struct pointer. And I'll call it thing. And just notice, this is the same syntax. We have the type, an asterisk, and then the name of the variable. If we want to allocate that struct, we have thing is equal to malloc, and then here I want to use size of struct, my struct. Now, to access inside of a structure, we would normally use dot notation, but since this is a pointer, we're going to use the arrow notation. And so B is a string, but keep in mind it's a character pointer. So we're not actually storing the string in the structure. We have a pointer to the string in the structure. So we need to allocate the string. So you put your name here. That's an important thing to keep in mind. And this is where C can get complicated. We've allocated memory for that string and then assigned that pointer to B that's inside the structure. So if I printf the structure, I'll do it size first. And A is equal to an integer, B is equal to a string. In fact, let's do the memory location as well. We'll do size of thing. And print thing A and thing B out. And once we're done, we're going to want a free thing. However, again, C gets tricky. We also allocated memory for thing B, which is a string. So we need to free thing B because that has a pointer that has allocated memory to it. So I need to spell that right. So there you can see we've allocated our structure. I think that should be okay. And you can see that this is the memory that thing is pointing to. Its thing itself is 8 bytes, but keep in mind it's pointing to a structure that's going to actually be larger than that. That's the size of thing. In fact, maybe that could be confusing. So I don't want you to get hung up on that. Thing is a pointer, so its size is a pointer, but it's pointing to memory that's however many bytes we allocated. So be careful that when you use size of that you're not expecting it to do something it doesn't do. So that's a couple examples of how to allocate memory in C. We won't be doing a lot of memory allocation at first, but your project is going to require you to allocate memory. So make sure that you get a good handle on this before you get started on the project. Oh, also one other thing I'll mention. Sometimes people will say that this is not needed. And in fact, technically it's not in this case because our program exits immediately after. However, I think it's always a good practice to free anything you've used. So for example, suppose I copied and pasted this into a function somewhere, or this in a function somewhere. I don't have the free statements. Now I have a memory leak. Sure, here I don't need to free it because this is all allocated in main, but it's best not to think about, do I need to free this or not? It's best to think, always free resources you allocate. This was a long video, but we covered a lot of material here. I think once you understand what's going on in this video, I think allocating memory should make sense, and especially focus on here with thing B. We had to treat it a little bit differently because this function returns us a pointer that is allocated, and we need to make sure that we get that freed.